Thank you for being here, everybody. Today we have a talk by Zeeshan Saeed. The title of the talk is on the response of free surface perturbed by positively-buoyant vertical jet. A little bit about Zeeshan. Zeeshan is a final year PhD candidate in mechanical engineering at UNH, and he's working on surfacing and mixing dynamics of turbulent buoyant plumes. He received his master's degree in mechanical engineering from Oklahoma State University in 2019, and he has one of the coolest introductions type of thing. Okay.
Thank you, everyone. May you know my name is Saeed. Today is my turn to present some of the work that I've been doing. The work that I'm going to present today is actually what I've been doing for the past year and a half or so, and is the fourth chapter of my dissertation, which I'm going to present in a few weeks. And it basically talks about, examines the response of a free surface, as you see what's happening on the slide right now. So to begin with the presentation, I'll first give you a brief outline. I'll first be going over the motivation and the objectives of the study, so why free surfaces are really important, and what are the specific questions that I'm trying to address this afternoon. And then I'll move on to the experimental methods, which comprises the setup that I've used, test conditions or the condition metrics, and how I process the data to get the required information that I want. I also would then present some results, which I will analyze. And this is where it will get mathematically involved, but I'll try to keep it to the minimum. And then finally, I conclude with conclusions and future research questions. Tracy gets to hire and who's interested in working with this. So to begin with, the geophysical relevance of free surface, indirectly, what you have over here is an active submarine volcano, and they're known to spew mantle-derived solute into our ocean waters. So it is of interest to know, what they're doing, but you can also appreciate that the situation can be a bit explosive, and it's dangerous to, get around these things. And if they're really close to the surface, they do have the potential to emerge at the surface, just like the one that, the introduction slide have. They can create surface emergent patterns. Similarly, hydrothermal vents, pretty similar to volcanoes, they do the same stuff. And if they're really close to the surface, shallow conditions, they can also have surface emergent patterns. And then finally, we have discharge of subglacial meltwater. Glaciers melt. And speaking of which, I have this video. So if you see over here, there is this marine terminating glacier, and then there's a discharge of subglacial meltwater that is emerging at the surface. And most of you would agree if I said that I would not want to dive in and see what's happening underneath the surface, because things can collapse and that would be the end. So it is, one can appreciate that the problem is, at least with regards to collecting in situ measurements, it's dangerous, it's time consuming, and it's also expensive. So, and what we can also appreciate is that if we are able to analyze how these surface patterns move, we do have a potential of using free surfaces for remotely assessing subsurface flows. Okay. Now, this was the motivation, but the specific question that I'm trying to address really is this: how does the free surface respond when perturbed by a submerged jet? It's more like an umbrella question. What this entails is that it also requires identifying unifying features, because it would be nice to see if there are any unifying features of this response. And then it is also of interest to examine how these unifying features relate to the source properties, which is obviously not apparent, but could be at some distance beneath the free surface. And then it's also, and this is where I'll try to get more conceptual. What is this? What do the results speak about the nature of the free surface in itself? How does it, cater the flow that's been thrown at it? Okay. So to address these questions, I have a relatively simple experimental setup, but it's very effective. What I have over here is plume fluid, which is at 50 degrees Celsius, so pretty hot. And then what I have in this large tank is ambient fluid at 4 degrees Celsius. And then I also have a source of in a diameter of 0.66 millimeters. And the tank is relatively large compared to the source size, so just so that I can mimic real life conditions as much as I can in a lab, the flow does not really get interfered with the sidewalls. So that's the reason of selecting a relatively large tank. And then I have an insulated tubing, insulated because I need to preserve temperature differences, which I'll explain later. And there's a pump, there's a shock valve to turn on and off the flow. And then there's a throttle valve to adjust the flow rate that I want. Okay. And then there's a flow rate meter, and then there's an inline thermometer that's giving me real-time measurements for the temperature of the fluid that's being fed. And out comes this plume. It ultimately hits the free surface at a certain distance, but then up top, there's an infrared sensor, and that is capturing the images that I was running earlier on. Now, the image acquisition rate was around 50 hertz, exactly at 50 hertz, and was kept constant. And the variables, the primary variables, there were two variables. One was the distance between the source and the free surface, and the other one was the velocity of the flow at the source. So that is achieved by adjusting the flow rate through the throttle valve. And what this led to was Reynolds number ranging from 600 to around 10,000. So around 2 orders of magnitude difference between the separation between the conditions. And then I have a source-based Richardson number, which varies from a very small number to somewhat of a small number, but nonetheless, it is accounting for the point effects to a certain degree. Now, I do have a buoyant jet, and in this regard, it is a bit different than a pure plume and a pure jet. Everything is driven by buoyancy, and in a pure jet, everything is driven by momentum. And rarely it is that in practice we encounter a pure plume or a pure jet. There are almost always some temperature differences that are influencing the flow. So there is a region that becomes obvious that there's a transition region that sort of the system has been updated. So we have a source, and the flow emanates, and then beyond certain region, buoyancy takes over. So momentum sort of fades away, and the dynamics is really driven by the buoyancy beyond certain height or downstream distance from the source. And this distance is determined by the model length scale. And what this model length scale is essentially is that it is a source determined length scale based on the momentum flux at the source and the buoyancy flux at the source. So it's basically how much of what is the relative influence of buoyancy and momentum that's been set by the source conditions. This is what this length scale is doing or helping me characterize. So based on the setup of the test conditions, what I have here is a jet. So my conditions range from a very jet-like regime to a plume-like regime. Okay, so there was a good mix of conditions.
Let me get that off the screen for you.
Absolutely.
Sorry.
That's helpful. And then the entire range of the conditions that I have for these experiments had such that the free surface was in the far field of the jet, or far away from the source, if you may. And then the Reynolds number and the Richardson number. What's important to note here is that the free surface perturbations were gravity stabilized. So it was not a vigorously perturbed free surface in the sense that the perturbations were very strong, but they were mostly dominated by gravity and they were stabilized by gravity. That is affected by the small Proud number. And then the Weber's number sort of customary over here because everything is controlled by the gravity and not the surface tension. And then conditions ranging from, as I said, pure jet to pure plume like conditions. And then each condition was repeated around 5 times, so 45 set of different experiments. Just trying to ascertain if things can be replicated or results can be replicated. Having done the experiments, the first order of business is to ascertain what's the quality of the data. And what I do is that I pick a time series of pixels and I compute its Ph.D curve. And I do that for every single time series, for every single pixel location, and I average them to get this curve. This is the Ph.D curve. And over here, there's certain distinct features. For instance, my primary signal might be around this, and within this region, and then slowly the noise sort of starts creeping in. Now, in order to determine what's the cutoff frequency where I don't rely expect my data to behave well is determined by fitting this line through or power law through this spectrum. And it tends to deviate from the spectrum, the Ph.D. curve at a certain point. And that turns out to be my cutoff frequency. And based on that, I estimate my noise flow. So what I do next is that I compute the total variance between the minimum frequency and the cutoff frequency. And I also estimate the noise based on the noise flow or the procedure that I just mentioned. And then I compute what's my expected flow part of the signal. So it's giving me what percentage of the signal is relevant. The reason why you're seeing such high values is because of the high temperature differences that I have from the beginning. As Nathan, I don't know if he is here, but as he would put it, I've juiced up the signal by increasing the temperature differences. Okay? And that's essential because if I want to get reliable data, I need to have low noise in my brain. This serves as an input for the next step of the process, which is to use this threshold for orthogonally decomposed modes. For this, I'm using proper orthogonal decomposition. Proper orthogonal decomposition, it is essentially a reduced order model that extracts dominant features and helps filtering out the higher mode or less energetic features, which are just there because noise can be nuisance. It can be polluting the data, but it can be contributing in terms of the energy if the measurements are sufficiently reliable. So what I do is that I stack all thermal images into a data matrix, and I then subtract the temporal mean, get the fluctuating data, and compute the covariance matrix. And here I essentially pose the problem as an eigenvalue problem. I get eigenvectors and eigenmodes, and those eigenmodes or eigenvalues are the modes that I'm interested in. And then I retain the number of modes required to capture cumulative energy corresponding to the pure part of the signal. And then I finally project the data to reconstruct my denoised version of denoised images. And what comes out is this. Okay. So this particular condition was taken at 35 diameters downstream from the source, and the resolution was around 0.6 millimeters to a pixel. And as you can see, the features are very distinct. There is, as the flow sort of evolves, the features also keep changing. But the important point over here is to note that this is temperature information. I've just stitched together several images. This creates an illusion. I may know how fast or slow these patterns are moving, but that's not the case for here. Okay. So, if you may have also noticed, is that the flow is evolving as if it is more suited for a polar coordinate system. It is evolving in circles. The problem, there's a mismatch, and the mismatch is that my pixel distribution are Cartesian. So I have my pixel location, I have Cartesian coordinates mapping to where those pixel locations are and what's the temperature value. And that's sort of problematic because the flow wants itself to be analyzed in a polar coordinates and not in a Cartesian coordinate system, as one can appreciate from with regards to how the patterns are moving in real time. Okay. What I do for this is that I transform this I decompose the image into a bunch of concentric rings and rays. That's the most natural approach for transforming into a polar grid. And what I get is this image. So this is basically this image, but within a certain region, and it's decomposed, and it's been reconstructed by decomposing this image into a bunch of rings and rays through radial and angular discretization. Okay. I'm also interpolating, and that's a problem because it can be a problem because if I'm just creating information from my own, that's not really representative of what's happening in real life. Okay, so I need to be able to determine if that interpolation process is really reliable. Okay, so for this, what I do is that I take this image, I reconstruct a Cartesian image, and I compare the original image and the reconstructed Cartesian image. And what I do here is that I plot the RMSE with respect to the NETD, which is basically the noise equivalent temperature difference of the sensor that I'm using to capture my data in the first place. And as you can see, It's very well below the noise floor, at least half that of the noise floor, the inherent sensor, which was in itself very low because of the strong temperature differences that I have to begin with. And then what you have over here is basically a summary of what the whole data set looks like. For any, there was just one condition for which this interpolation error got as significant as the noise floor, but since the noise floor itself was pretty weak, so it wasn't really affecting. It was telling me that I'm not introducing information of my own, mathematical artifacts. It's whatever the data is, showing me. Okay, the next part of the problem is to be able to track these patterns. As I said, this is just temperature information, and this is not velocity information. I don't have any quantitative velocity information. Visualize it to be moving. That does not mean that I have values for the velocity of how these patterns are moving. Now, if any one of you is familiar with how this is typically done in PIV and stuff, what we have in typical PIV is that we see the fluid by like tiny particles, have them shine in a laser sheet, and then get these images and track them in real time. But the problem, the difference between that scenario and the one that I have right now is that those seeding particles are discrete and they preserve the structure. They're not getting squished around by the flow. On the contrary, what thermal field is doing that it is obviously the thermal patterns are moving, they're changing their appearance. They twist and fold and turn, change their appearance. And since this is a free surface, it's also losing heat. That could be due to evaporative effects, and that certainly is due to radiative effects because that is what my primary signal is. I'm relying on radiative effects just so that my camera can see how the flow looks like. So those are the two challenges. And the other one is that they are space continuous. They're not discrete. Every pixel has a certain temperature value. It's not discrete. So essentially the problem, the mini problem that I have is that I need to be able to determine if the thermal patterns can be reliably traced with sufficient resolution to get velocity information. So that's not a first-hand information, but that's an extracted information that I'm trying to sort of reach for. For this, what I do over here is that I develop an autocorrelation function of the temperature value just so that I have some idea of what or how fast those temperature patterns are fading. Okay. Now, this is a autocorrelation, temporal autocorrelation curves for the two conditions, for all the conditions, but really for the condition with the largest time scale and the smallest time scale. And everything in between this shaded curve is whatever is for the remaining conditions. One can define however they want to in terms of like what is the characteristic scale. It can be the zero crossing, it can be the e-folding, it could be 1/2, it could be whatever. But really in that sense, the time scale that I'm interested in is the time separation between two consecutive images because I'm tracking patterns from one image to the other. And that really corresponds to this, the first lag point, which is pretty close to 1 as confirmed in this plot. So what this is telling me is that those thermal patterns are also acting as passive traces. I can track them without having to fear that they might have changed from one image to the other, such that they cannot be recognizable. That will affect the correlation status. So now that I've established that thermal patterns are passive traces, I need to be able to determine or find a mechanism of being able to resolve the velocity vectors with sufficient resolution, and that is what comes in next with sufficient reliability. So say I have a denoised image. Okay. I'm developing this heat. I'm using certain filters to break this image into discrete spectral-like structures, and for that I'm using two filters. And based on how those filters move, on how those filters move in real space or real time, I develop this heat map. Now I'll explain how I get this heat map. For instance, revert back to this image. If I have this image and I'm using certain sizes for the two filters, it could be any filter size. It could be small filter size, it could be large, it could be a whole mix. But that really affects the reliability of the velocity vectors that I'm creating. For instance, if I have this image and I use very small filter sizes, I get an image that looks like this. It's basically tiny speckles of dust or something. But the problem is that when I'm tracking and I can track and it will give me some velocities, some values, but those won't be reliable enough. Okay, because what that would mean is that it is I'm getting velocity vectors based on this correlation statistics. Now you may have 100% vision, but it's really hard to figure out where the primary peak is. I don't know where the primary peak is because it's just embedded in the noise. It's as good as noise, or it's as good as ground. So, and that's with the very small filter size of 2 pixels for each. If I go for a very large filter size, I'll create proportionately larger patterns, thermal patterns for my pre-processed images. There are two issues. One, if I track them, I'll get a primary peak, which is much improved, but then there's only a primary peak. I can't really identify what the noise floor is. And all that's primarily because the quality of this peak is poor. It's taking very many pixels to probably die down to a certain threshold, say half of its value. Okay. And the other problem is I don't have any information between these dark patches. So what I will end up doing is that I will interpolate whatever information is, and that's made up information, not layered information. That's also the thing that I want. So Clahe and high pass filters of 200 pixels, bad. So one has to go iteratively, block by block, for all the filter sizes to obtain an image that looks like this. What this gives me when I'm tracking velocity vectors is this primary peak, which is distinct from the noise, but also going down pretty fast. So that is the algorithm is pretty confident in detecting a velocity vector at that spot. Okay. And this was with a filter size of 13 pixels and 12 pixels, initial interrogation window 64, and final of 48 pixels. Okay, so that is how I get this point. So block by block, this heat map is generated by estimating how reliable the velocity vectors are. And then eventually what I get is this instantaneous image. So this is instantaneous flow field corresponding to this image. When this image is transformed or pre-processed using this filter combination, we yield this. So this is how I obtain my velocity fields, even though they may not be directly available by just looking at the thermal images. Okay, so I'll now move on to the temperature velocity field. What I've done, if you may remember from few slides ago, what I've done is that I've decomposed this image into a bunch of rings and rays. Okay, now I would want to consider the data of this particular ring, concentric ring. And for this, the center point of this ring is basically determined by averaging all the images and picking the mean representative image and finding the spot where the value is the maximum. So that tells me that the center point is anchored to the flow dynamics and not my own personal biases. What I do is that I compute the mean, I compute the fluctuations, I get the correlation in the zero lag, normalized autocorrelation function. But then what I do is that I compute this correlation over 10 consecutive rings, and then I basically average those curves to see where does it go to 1 over E of its initial value. Okay, and that would be the correlation angular scale along the angular direction for that particular radius, and that is how I developed the angular correlation scale, or the radial profile of the angular correlation scale across the entire image. What comes out is this. You see that the free surface induced shading essentially curves the geometric growth, because this red point corresponds to that which is where the flow rate is the maximum and also the free surface is nearer. So the flow is impinging the free surface with more force. Okay? That sort of tends to reduce, or there's more. If I'm comparing conditions at the same source velocity but different heights, so I'm essentially varying the height of the free surface by maintaining the same source velocity, I see that the source of the separation promotes the geometric growth of the angular scales. The growth in the scales is less restricted, because if you compare this with this, obviously that difference is apparent. Okay. I do the same for the radial scales. This time, I have information along the radial rays, and I do the similar correlation fluctuation stuff to get the correlation scales along this direction, and that every single angular distribution as extend over every single angular distribution from 0 to 2 pi. And what comes out is this. You can see that if I'm increasing the radial footprint shrinks if I I'm increasing the force with which the flow is hitting the free surface. And this is apparent by this darker circle as compared to the lighter red circle, similarly for the blue curves. If I'm increasing the separation between the source and the flow by maintaining this source velocity the same, the radial footprint is increasing, as you can see. And that has to do because I'm allowing more space for the jet to develop. And as that is done, it's entraining more and more from its surrounding, and it grows. And that's why you see that this blue curve, which is at a farther height than the red curve, is much farther off. The radial, the definition of the correlation length scale is obviously biased because I've taken 1/8. I may have taken the zero crossing or the half or whatever, but that again, it doesn't really affect the conclusions that I'm trying to make over here. Similarly, so just to put it in words, radial footprint grows with increasing source surface separation. This was for the thermal temperature field. For the mean flow field, what I have is the mean velocities at first. So you can see that the mean flow field is getting intensified if I'm increasing the source momentum flux or I'm increasing the source velocity. Okay. The profiles are getting sharper, and this is consistent across different heights. Okay. And if I'm just comparing conditions with different heights but same source velocity, I see that the mean flow field broadens and is getting weakened in terms of its magnitude, but it's also moving farther out from the region. And that region is the stagnation point that I determined that I showed a few slides ago in my quick plot. Okay. If I take the radial gradients of these profiles, this is what follows. Okay. Radial strains intensify with increasing source momentum flux, but what you can distinctly recognize is that they all seem to cross the zero crossing at the same point. Okay. This is consistent for different heights, and this is more apparent. And what this means is that the mean flow scales or the length scales are insensitive to the momentum flux. And this is more apparent over here because now I have conditions that have fixed source velocity, but different separation, but increasing separation between the source and the free surface. And you can see that the zero crossing is progressively moving upwards. And this essentially means that the radial strains are weakening with increasing source of separation. And again, consistent with the radial scales, the flow is allowed to train more and grow more, and therefore also have a larger radial footprint. With flow in a polar geometry, you also have angular strains that come from radial velocities and radial coordinates. And this is what this is. It's basically the radial velocity divided by the radial equation. I've omitted the first data point because that obviously means I'm dividing by zero, and that's singularity. Okay, that's not good. So I'm just omitting that, and that would have yielded me an unphysical point. Anyways, what you can see over here is that the angular strains intensify. You can see the values are sort of increasing, but getting progressively smaller as I'm sort of reducing this velocity of the jet at the source. Then the angular strains also weaken with increasing source surface separation. The source surface separation increases downwards, as shown by the arrows. And the distinct point over here is that the angular strains remain positive. The radial strains may become extensional and compression. But the angular strains are positive because the flow is always moving radially outwards. So the radial coordinate cannot be zero. So the mean velocities are always larger than zero for an strongly upwelling flow. For the turbulent flow field, I have the URMS, the fluctuations, and this is telling me basically what's the intensity of the turbulent field. And consistent with my mean profiles, they follow a different shape. but they follow the same trend in the sense that the fluctuations are increasing if I'm increasing the source velocity at different rates. And this is what the two plots on the top show. And then if I'm increasing the surface height and fixing the source velocity, the turbulent flow scales grow with increasing source of separation. Okay. That's basically the highlight knowledge. Since I also have an angular field, I have angular strains. So angular strains are involved in producing angular fluctuations. And those angular fluctuations behave in a way similar to how radial fluctuations behave. Again, having different profile, but similar trends. And what I show over here is that the angular velocity fluctuations intensify with increasing source momentum flux. And what I show on the plots at the bottom is that if I'm increasing the source of separation, the angular fluctuations will decrease. But what I also see is that it's mostly that the magnitude of the fluctuations, the angular fluctuations and the radial fluctuations, they remain more or less the same. And this has to do with this is tiltating whatever is going to be in the next few slides. But what I'm trying to imply here is that the free surface is not imposing any angular forcing. It is respecting the structure of the flow that comes in. I have a round jet. I don't have any planar jet. So it's respecting the geometry of the jet that's been, fed to it. What I also have over here is the turbulence production term. So consistent, just as a customary sense. Radial turbulence production intensifies if I'm increasing the source momentum flux. That is, if I'm maintaining the free surface at a fixed height, but sort of increasing the source velocity of the jet, making things more vigorous. And you can see that this pattern sort of enhances. What I can also see is that with increasing height, the production sort of goes down, but it's also moving farther outward. So this is again reinforcing my earlier conclusions that the radial scales are increasing as I'm sort of moving away and away from the source. So turbulent production scales grow with increasing source separation. And the last plot for the angular production of the turbulence profile, they follow this nothing out of the ordinary. They're just sort of reconfirming whatever we have been observing in the previous plots. Angular turbulence production intensifies with increasing source momentum flux. And if I'm increasing the separation, it's just only contributing in growing the scales of turbulence production so that the intensity with which the turbulence is being produced also diminishes. So that is it for the results. And also, so angular turbulence production remains positive. And that's primarily because the strains are positive. So it's no negative, and that's, probably trivial in that sense. Now, what I need to stress upon is the mean profiles. As you may remember a few slides ago, I showed these mean profiles. What I'm trying to do over here is that I'm trying to pick a characteristic velocity scale based on these mean profiles. And how I do is that I basically pick the maximum velocity from each of these profiles, okay? And then I take to be my characteristic velocity scale from normalizing my velocities, so just so that I can see if there is any unifying features of the response. And what I do with the length scale to scale my radial distances is that I pick the radial location where this maximum occurs. And what happens is that if I recalibrate my velocities, everything collapses onto a single curve. So in that sense, the curves, the velocity scales that I'm identifying are some sort of a unifying, there's in some way unifying the description of the free surface response. You can also identify a region of linear growth. It appears to be a linear growth. I will prove this in a bit. And there's also a region of there's also this outer region where it sort of tends to decay. And this is natural because you can't really, you have a quiescent flow far away. It has to respect to its boundary conditions too. So it will increase and then sort of realize that it can't really go on forever. So it will have to decay sooner or later. And it decays such that this switch between whatever the mechanisms are is happening by definition at the identified length scale. If I do that for the mean strains, the radius strains and the angle strains, they also collapse, except within this region. And that has nothing to do with the validity of this collapse. It only has to do with my limitations of the experimental data that I have. I have finite resolution, and distances very close to the origin means that I'm dividing the values with very small values, and that tends to amplify any numerical uncertainty in my velocity measurements. So that's what that scatter is about. What I do now is that I compare these characteristic scales, and I see how they're changing with different height. The characteristic length scale that I've identified is varying such that it grows linearly with the source of separation. I also see that this characteristic length scale does not really have any strong dependence on the Richardson number of the source, characterizing the strength of the buoyancy and moment fluxes. Now, if I combine the two parameters, what essentially I'm trying to do over here is that I'm combining this and this parameter into a single parameter, and the difference and the trends persist. Because what this parameter is that if you recall, I had a modern length scale that can be expressed as a combination of HOD times the square root of Richardson number. And again, with Richardson number, there's no strong dependence. And this curve that you see is has a pretty strong linear dependence as shown by the coefficient of determination. So essentially, this length scale varies with the source of separation. For the characteristic velocity scale, I do see some trend, and I'll go over these plots quickly. So what I do is that if I see these trends and if I combine the two trends in the same parameter, I do observe that the scale is changing. The velocity scale is both a function of how far the surface is from the source and also how strong the source is in terms of its buoyancy moment fluxes. So again, the coefficient of determination for this power law is pretty decent for experimental data. So source surface separation, it decays with the source surface separation. So the farther the flow has to go, the more it will decelerate because it is entraining its ambient the surrounding fluids. Okay, so reiterating the point, this characteristic velocity scale additionally depends on the buoyancy and moment of fluxes. Okay, so now what I'm trying to do over here is that I'm trying to sort of see the theory, and if I can't get anything out of it in terms of the physics, these are just the results. Okay. Self-similarity from first principles, and what this means is that I will revert back to the equations. But what I need to first clarify is the kind of a schematic that I have. You have a source with a certain temperature difference and velocity, and it grows until it hits the free surface. It grows in a manner which could be thought of as if a jet is evolving as if it's unaware of the free surface. So it's evolving freely. Okay? But then at a certain region from the free surface, it really starts feeling the effect of the free surface. It really gets to know that there is something, there's a barrier perhaps, which is not allowing it to move indefinitely into whatever the outer space. So, and what happens over here is that as the flow is sort of changing, as the flow is approaching, it sort of decelerates in the vertical direction and accelerates in the radial direction. That is what was creating that strongly upwelling pattern that we saw. And then we have a certain structure, the viscous layer and the source layer thickness. So basically what I'm trying to say over here is that the free surface is within the far field, so it's much, much far away in terms of theory. Okay. The perturbations, these perturbations are gravity stabilized. So the Froude number is essentially smaller than unity, much smaller than unity, as I've also shown in my condition metrics. And then the Reynolds number defined based on the characteristic scale is much larger than unity. And this is also confirmed by the data. And then there's a free surface H. What I have to work with is this equation. It's a pretty big one, but it could be rescaled in a way to have it more manageable. What I have is a free surface. Winds were taking it easy, so I don't have any stress or wind-induced stress. That means that the shear stresses could be related and could be related to each other. I also have a linearized kinematic boundary condition owing to the peak perturbations at the surface. Nothing strong. And then I also have some angular symmetry as confirmed by the data. I'm neglecting surface tension, and I'm just assuming that the pressure distribution is basically a distribution of how the perturbations are sort of distributed at the free surface. And then it's basically an empirical observation that this velocity scales with this characteristic velocity, and the radial gradients should also scale with the radial distances or the characteristic length scale that I've identified. Using this, what I get is some rescaling, and if I use this rescaling, essentially I can appreciate what terms are really dominant and what terms aren't really that dominant. Okay? So straight away I can appreciate that this factor, because the Reynolds number is very large, this goes away, this goes away, this goes away because this Froude number is very small. But then what I'm left with is this term, the pressure term, and the divergence of the turbulent stresses. So that is how I'm reducing my initially very big equation into somewhat of a more manageable form. And essentially I'm using this observation assumption, which is empirically driven. Okay, so what happens at the end is that I get this nice, still not nice, but still manageable, more manageable equation, which is a rescaled dimensional radial momentum equation. If I'm to work with this equation, I'm using certain, again, observations that I've made earlier, is that the velocity is scaling in a self-similar way. Okay, so there's some self-similar function which is defining the distribution of the velocity, regardless of how far the source is from the free surface and how strong it is in terms of its buoyancy, momentum, fluxes. And then it must also be respecting certain boundary conditions. Okay? So it is zero at the surface, at the origin. This is the stagnation point, and then it climbs up somewhat linearly, whatever. But it also has to decay to zero because nothing's moving infinitely far away. I also have to model my Reynolds stresses, which I do with my strain rates, and that's again assumed, confirmed with the data, that if these profiles are such similar, then the turbulent fluctuations should also be following some self-similar form. And then I've modeled my pressure using some function, which is not determined, but I will, again, it's not significant. Then what I have is that this self-similar equation, for self-similarity to hold, this must be on the same order of magnitude. Otherwise, the balance between different terms is going to be disrupted. So what this really tells me is that this term, this viscosity term should go like H1/3. It's required, and this is a requirement for self-similarity. This is not something that I'm putting up my own desire. This is if I am expecting a self-similar solution, which the data suggests that I should, then this should hold. Therefore, the equation that turns out to be is a large big equation that I had to begin with gets to a more manageable form. And it's self-preserving ODE governed by this self-similarity parameter. Again, if I'm analyzing this equation, I can see that very close to the origin. Now I've tried to solve this equation asymptotically, and I'm just saying what terms are really dominant way. Okay, so essentially, what makes these two terms really go big is because they're being divided by a very small number close to the origin. Okay, this is obviously the balance has to be maintained between the two, and this is a really nice first order ODE to solve. And what this does, and this sort of reminds me of what Arthur Conan Doyle speaks his mind through Sherlock Holmes. Singularity is almost invariably a clue. Okay, so singularity, the singular point, this point, whatever the self-similarity is, self-similarity parameter very close to the origin is essentially a singular point. Radial fluctuations or radial directions or even angular directions do not have any meaning at the origin. Okay, right at the origin. So R is equal to 0, whatever, this self-similarity parameter equal to 0 is a singular point. And this is what makes this is what makes the profile grow linearly right at the origin. If I'm comparing the terms that are really dominant far away, then I get this, again, this equation, and instead of pretend that this does not exist. And that has to do with the balance between the radial reflection and the turbulent transport. If I take these approximations and map it with the data, you see that it follows the data pretty nicely. So there's a linear growth at the origin and sort of an inverse decay far, far away from the origin. So what this tells me is that the free surface is passive. It is not introducing, it's respecting the structure of the flow, which is also sort of hinted towards in my earlier presentation of the results. This length scale R aesthetic, which is essentially where sort of the flow decides to die down, is also a crossover length scale. And this kinematic, not kinematic, but it's a eddy viscosity term. It behaves neither like a pure jet or a pure plume. Because had it been behaving like a pure jet, it would have been a constant, which it is not because it's obviously changing with height. And had it been behaving like a pure plume, it would have behaved with a power of 2/3, but it does not. And that again has to do with the fact that it's really hard to have a condition which is more like a pure jet or pure plume in practice. Okay. So that's and also typically it is neither of those. It's more like a idealization on paper or something, because the pure jet regime corresponds to this, and the pure plume regime corresponds to the large distances. Okay, so conclusions. Free surface response intensifies with a stronger source which is nearer to the surface, and vice versa. The characteristic length scales that are identified universally link the subsurface or the free surface flow with the subsurface flow, however you want to put it. The free surface does not impose additional scales. It's working with a self-similar structure of the jet that I didn't really have the time to go through, but that's essentially what I mean. And then these length scales, they objectively measure the momentum flux of the surface of the jet. Okay. Now, if I circle back to my original point, if you remember, I had this video running. If one were to look at these patterns and do a similar analysis that I did, one can estimate, one can certainly know that whatever the characteristic velocity scale is linked to how deep the source is and how strong the source is. And this is important because I just have a single metric. I don't have to run around the entire place looking for different metrics and parameters. It's just giving me a good metric to estimate what's happening. You and R star can estimate jet entrainment history, and this is a more advanced projection of the work that I've done, and this is what could be done in the future to explore, to do simultaneous EIV and free surfacing imaging and determine how do they relate, or how can these parameters be used to estimate the jet entrainment history. And it also ascertains how strong the one jet is, like what's the content, what's the temperature, and all those kind of details could be implemented. And before I end, I would like to sort of acknowledge a few people. I've been working on this thing for a long time. Tracy, Nathan was not here, but he's been kind enough to lend his ice maker for me to get some data. But I also want to acknowledge Chris. Chris is not here, but he's also had to do with how I develop thoughts and processing data and all that stuff. Folks at Fieldhouse, they generously gave me large amounts of ice, around 2 tons or something, over the span of 4 months. So thanks to them, and finally to my wife who helped me with my experiments. Yeah, so that would be it.
We have a minute for a few questions, if anybody has, please.
So most of the jets I've run into also have bubbles in training.
Yeah, that's more like in the regime of multi-phase flow. That's it. Yeah. Essentially, thermal imagery, I mean, as long as the temperature is the same, it really can't really distinguish the difference between it's not it does not rely on what's the different density, but what's the different temperature. So even if the bubble is at the same temperature, the water, it won't really pick it up. So that could be one of the, yeah, sure, that is one of the limitations. But
Doesn't change the buoyancy.
What?
Doesn't change the buoyancy calculation.
the thermal camera doesn't really care about points. It cares about the temperature differences. So if I say heat this part of the wood or whatever at a different temperature, and it will show me that this is at a different temperature and this is at a different temperature, even though they might be at the same density or something. So it doesn't really rely on density differences, just relying on temperature differences. And in the context of fluid mechanisms and stuff, in doing traditional velocimetry kind of stuff on free surfaces can be really challenging because you're relying on a laser sheet, and that's essentially a straight sheet. But the free surface won't really care about it. It will jump up and down, and it will create multiple problems like refractive index matching and total internal reflection. That's going to corrupt the data to a certain extent. So thermal imagery is really good in that sense that it's a non-intrusive technique that really looks at the free surface and gives you a good estimate.
I think the question was that the subsurface dynamics have changed. Is that correct? Like you have bubbles, so the buoyancy flux is different.
They
So,
expand as they go.
Yeah, so is it that, I guess
They might even burst. They could, but I mean,
but
Yeah,
then,
I mean, you can have buoyancy without any temperature.
yeah, salinity, for instance, it won't be able to, but essentially the idea is that whether the buoyancy is temperature driven or salinity driven, it is likely to impact the flow in the same way because it's reinforcing the mean flow, the mechanisms by which it sort of integrates the flow and the turbulent aspect of it is the same regardless of whether it's generated by salinity or buoyancy or temperatures. Yeah. I don't know. Oh, you can go.
So you, thank you, by the way,
Yeah.
you made the assumption that there's no wind stress,
Those what?
no wind stress.
Yeah, yes. Surface is
What
free.
happens in the ocean?
Yeah,
And
that's-
surface waters, is that, do you see that those types of surface influences, would they be difficult to deal with?
It certainly is difficult because then you will have to have a different framework to deal with the theory. Because right now I found a really nice way to sort of manage my equations and rescale them and get a nice pretty little interpretation, but that might not be the case if say the waves are big and really
Even in a situation like that, where
Yeah.
we can assume that there's no surface.
Well, that would really depend on what the perturbation is relative to the largest length scale. So say if the wave is like 10 feet big or something, that's going to be problematic. But over here, if it's like say 3 centimeters or 5 centimeters of for surface perturbation, the characteristic length scale is likely to be much larger than that. And so it really is a balance between two distinct length scales, I think. Okay.
I was just curious if you, or to follow up on the previous question, like, did you notice bubbles in the jet?
No, I
in
didn't.
your experiments?
So what I did was that I primed the apparatus, so I ran it for like good 40 minutes prior to the start of the experiments. So there are no trap air bubbles.
That makes sense.
I don't want to make my life more difficult. So, just decided not to do that. But yeah, bubbles are encountered in practice. And yeah, they
So would
can.
that just like modify your equation a little bit? You'd have to
Of course. I mean, you have multi-phase flow. You have a trap in a certain region that's behaving in a way different than the rest of it. So I guess it is likely to, win the show. Yeah.
I have two quick questions. See, in the turbulent production field plots, what does the negative values mean?
It's basically meaning that the strains are compressive. That's why it is sort of. It doesn't really mean that there is a net transfer of production to whatever from turbulent component to the mean. It really means that the accumulated production will still be positive because if I'm to sort of integrate that whole curve, it would stay. The production would dominate over compression, And that's typical because, there is and that's really a consequence of the compressive strains.
Follow-up question, the pressure strain correlation near the surface, how did you detangle the pressure and the strain that's correlated near the surface, or which transfers the
The
energy?
pressure strain would come into a more advanced version of the TKEs. I mean, for instance, the TKE equation. But I'm dealing with the highest of, so just momentum. So that would just be pressure gradients, right? I mean, there are different ways to maybe like let's to keep it simple.
How computationally expensive is it to run these filters and computations?
I was actually discussing with this with Tracy this morning. I think computationally, what you would have to do is that you would have to simulate a jet which is far away from the free surface. You'll also have to be.
I think he was asking about the processing.
Yeah,
processing?
the processing itself.
Yeah.
Just like looking at doing a real-time version of this for like depth estimations, like how computationally expensive would it be to do that?
But it's just I mean, you don't have to have soft phase if the model is pretty well developed, and if this can be further developed, you can use the connection between this length scale aesthetic, what R aesthetic with the height. Given that the coefficient that is giving you the precise value is also very well determined.
Okay.
So that would be one of the things. But it's expected to grow linearly with height. So that's.
If we have further questions, thank you to our speaker on the line.